All right, so I suppose we'll begin. So today we're going to talk about practical applications of virtual machine introspection. You guys have heard quite a bit already from Tomas, with whom we work fairly closely. And hopefully it'll become more apparent that after our presentation, there are greater applications beyond security. It's certainly a security-focused feature in most hypervisors, but the spectrum with which it can be applied is actually quite broad. So we are Zentific. We have a couple members actually present here today. I'm Steve Maresca, and this is Russ Jancewicz. I'm the benevolent dictator, I suppose. But we have quite a few things that we do, namely security, certainly, but we do want to disclaim that the point of this talk is not to go over that. Hopefully, we will avoid mentioning anything regarding rootkits or malware or something to that nature.
So just going to go through this basic agenda. We're going to cover the introduction into virtual machine introspection. Tomas gave a really quick overview from what I could see through the door, but we want to kind of go over a little bit more detail there. Then we're going to look at Zen-specific features that make it really kind of slick and help us out when we're doing things. As Steve said, this talk is going to be predominantly not about security, which is different for us, but it goes into a lot of details there. We're going to go through some of the data access techniques in VMI, and then give a couple use cases, show some tools, and time permitting and demo gods permitting, we will actually do some demos.
All right, so what we've done and why we're here is because we have employed virtual machine introspection for security. In essence, basically the same demo that Tomas supplied. Same vein, ignore it. It's a marketing slide. We don't actually want to talk about that at the moment. But that's why we're in this field. We started in security. That's our background. We're security researchers first and foremost. But just because VMI has a long history in the security world, and we're talking 2003 from the first academic papers on x86, but IBM, for example, with its mainframes, VMI is essentially baked into all of its hardware, all of its hypervisors, ZVM, from a literal silicon level, because they're in control of the full stack at that point, so we don't need to play these games with peering into one context from another. It's already enforced at a policy level. Other companies today, we have Virtuata, Bromium, though they would prefer that you think they're not doing introspection, Trend Micro, McAfee, Counterattack, quite a few others. It's not a very sexy marketing term, so we tend to avoid it in the world, but they're certainly out there. So VMI, as Tomas gave a nice overview, is in-depth view of a virtual machine state. We access the memory, the CPU contexts. We can handle EPT violations, register changes, register writes, and so forth. In particular, it's a very low-level feature, very similar to debugging. As a result, there are a lot of systems which use it at a low level, and that means that it's fairly cumbersome, which is unfortunate because we're all familiar with debugging. We use debuggers on a daily basis, probably more than we would like, depending upon the types of problems. But ultimately, when we're looking inside of a virtual machine from an external vantage point, there's a great amount of state that we need to reconstruct. And while architectural specifications help us to do so, it's a lot of work when typically we work with debuggers that have operating systems helping them out and getting into process memory and so forth.
So, as Steve was saying, VMI is essentially just a debugging tool for us. We don't have the assistance of the OS, though. We are looking at things from a black box, and we are trying to reconstruct our view of the OS externally. It's very akin to JTAG debugging. You have ability to request an address and get information out, but you don't really have access to typical coding structures where you can just dereference things and they magically appear. But because of this, it becomes a little more difficult in terms of getting information out. We have to do reverse engineering a lot of the time in order to figure out where structures lie, how to access them, how they change through versions of the OS, through versions of simple programs, through patches. Every single kernel update has a new system map, so we have to go get that information if we want to be able to access the data in a consistent way. So the issue here isn't, though, that we can't do this. There is no technical limitation. It's that there haven't been convenient tools for us to do this in the past. But what we've had with Zen and with the ability to, implement these features using the techniques Tomas has covered, we're able to leverage higher end tools to dive down into this data.
Academia referenced that as the semantic gap, which is a delightful term, I suppose, but it's really that the development skills of some researchers haven't necessarily exposed them to the necessary features to actually dive into the data. But it's certainly a possibility, and that's really what we make use of.
All right. So VMI is possible with most, if not all, hypervisors on the market today. At minimum, you need to be able to access and read memory, and from there you can reconstruct a lot of the stuff that's inside the system. The idea is it kind of mimics tools that are used for forensic analysis, but doing it live and being able to access the data as quickly as possible. Ideally, we do want more information. When we are looking at registers, we're able to react more quickly. We're able to check different directly access structures like the page tables through the CR3 register. Zen just happens to make this really nice and easy for us. So
Zen being particularly well suited for VMI is a simple state of affairs. It's actively being developed by people who are working with VMI. That's not necessarily true with something like VirtualBox. That's user-facing. It has the facilities. You can read into VM memory. VMware does too. You have to pay to play. Zen being out in the open and always pushing the envelope in terms of features is a wonderful place to be if you're a researcher and building third-party software. Now, the API that Tomas provided a history of has certainly been subject to a lot of churn, but its current state is stable. Its current state is exceptionally usable, and even if it were 2 or 3 versions ago, provided that you were looking into process tables or something like that, process lists, you're quite good. Zen security modules in particular facilitate isolation that is rather important if you're looking into virtual machines. If you have a number of guests which are themselves owned by a certain number of tenants, you need to isolate group A from B such that your omniscient observer from the hypervisor perspective can't see into the other customer's VMs. Customer, department, user, however you want to bake it, XSM gets you there. It's not necessarily absent from other hypervisors. KVM certainly can use SE Linux and similar facilities, but Zen is by far the most mature in this particular area. Now, Zen events we talked about a moment ago. We won't really spend too much time over this. You know already from the previous talk. But bottom line is, VMI is not really for not just for security. If it's interpreted as something that you can use like debugging, it's as open-ended. You can use VMI for failure triage. If you use crash for core dumps from Linux, you've actually used a form of the same analysis. You're looking into page tables of a virtual machine. You're reading process lists, loaded modules, CPU context at the time in the ELF core dump. It's essentially the same thing. But why not go deeper? You can certainly look into the applications that are running themselves. You can look into CPU performance variables. You can take a look at structures in memory which are themselves recording the state of the machine and its usage. Because VMs are not opaque containers, despite the fact that most of the management tools we use treat them as such, we can prove that VMs are transparent items in a virtual machine. VMs are transparent containers in an actual system, which permits us to get all of the information we want out of them. Some examples of this include listing running processes, scanning for hidden processes, printing kernel buffers. We can take a look at syslog, for example, host name, listing processes as they start and exit, actually at that moment. We can assess system statistics, entropy available as a great one. I mean, virtual machines certainly suffer from entropy starvation, so why not assess that across your entire infrastructure? Open files, logged in users, print socket flags, and so forth. These things are certainly capable within an operating system, but if you're looking at thousands of them, why run thousands of agents to get at the same information? It's just consuming resources. It's just additional automation. And hypervisors provide a route to getting at some of the more detailed data.
So with VMI, there are some obstacles to the practicality. The first and foremost, it is a black box. Like I said before, you have to dive into it with external knowledge to the system. Luckily, this can be solved pretty easily with debug information. We're able to extract from public sources for Windows, for Linux, and it lets us get into the base structures, and then we have to do a little bit more legwork there ourselves. It also is hampered by the fact that we don't have the OSA to debugging. We are doing this by hand. We are doing this ourselves. So it is a timely process currently. It requires a little bit of effort in order to access this information. And like I said before, we do have to maintain that external state ourselves. So we can utilize a lot of this debugging information that we have. The key here is it doesn't need to be used inside a debugger. Dwarf files, PDBs, these are available to us just through simple sources, and we can extract the information within them. Sometimes they're harder to get to, but Microsoft and Google, for example, provide these. You can just download them. This allows us to build representations through what they've provided and told us to be authoritatively true for their applications in order for us to inspect applications or operating systems.
Now certainly, it might be tempting to ask why VMI is something that you'd want to pursue if we already have debugging facilities available. VMware has a GDB stub, Zen has a GDB stub, and that's great after all. But I'm not really sure how many people have used the GDB serial protocol, but it's hideously slow, and it's not necessarily something that lends itself to performance. Plus, you run into problems with OS agnosticism at that point. You want to treat your VMs as independent, generic things. So you might as well treat them with the tools that you have with a generic perspective. The debug stubs that we have don't necessarily permit us to do that.
All right, so basic view into how we are conducting VMI at this time. It all takes place using the RAM and virtual CPU settings that we have. We're accessible through the Zen APIs. We can reconstruct pages, access the virtual memory, and basically traverse down as the operating system would do for you internally into a specific object or data structure, and then access the members within it. So for the previous example, just real quick, that data structure there, we don't know what's inside of it right now. It is literally a box. So a perfect example of that is the task struct. So if we want to get in there, we're able to use things like PAA hole, dwarf dump, object dump, and reconstruct that box into something that we're familiar with. And using the offsets and using the sizes, we're able to read that information back out, simply knowing an address and having this accessible debug information provided to us. So here's an example of typical VMI for task iteration. Basically, we want to go through every task that's running inside inside of a Linux VM. It's going to start at task 0, which does exist. It is just hidden from most systems when you first run. The init task is the one that's displayed. But it will continue through by taking the offset of the kernel list, looking up the location of the next pointer, and then moving up to the head of that object in the memory. So this is a very manual process. You have to take the object, you have to look up the offset, you have to look up the offset to go back from the list object. Same thing will happen inside of Windows. You're able to do with just a different structure. It's same list walking, same general format. Another example here we have is extracting the host name from a Linux system. The init UTSNS is the structure which holds this, and we just have to request the offsets of these members and then dereference it. that gives us our char star. The native C equivalent to this would simply be taking the member out. And so it's a very simple process when you look at it as C, but it has a lot more overhead when you're looking at it as the VMI, but it's still accessible when you add tools on top of it.
And if it's at all unclear, one of the things to keep in mind is that when you are accessing non-local memory, you lack the primitives that are typical in C. You can't simply access a member of a member of a member and then dereference it. The fact is that it's not in your memory space. The address value is nonsensical for where you're actually introspecting. As a result, you need to take these additional steps. It's not necessarily cumbersome, provided that you know what data you're interacting with, but certainly the layout is something that you need to keep in mind. PA hole being something which helps to show holes in structures just happens to be convenient for this type of work. Now, the benefits of VMI in general are efficient access to VM state, simply because you can see both the kernel and all applications at the same time. It's a fairly unique place to be, and it's a pleasant one in that you don't necessarily need to be switching gears quite a bit. You have everything at the same time. You don't have to deploy agents. You don't have to integrate with the virtual machines themselves. It's simply less complexity. You've moved it into your monitor. Now, we don't really have a choice. In some deployment mechanisms, you actually require something like this. Containers themselves have a goal which is to be as slim as possible. And unless the application running within actually supplies its own monitoring and logging facilities, or, for example, it has a particular value in a variable that you want to look at that isn't exposed, you need to use something like this or you don't have any other choice.
A great example of this is Docker. The container con is right there. They have accessibility into the logs for Docker systems very easily through the Docker interface, but extracting that out for regular access and monitoring is a cumbersome task, and there have been projects that have to change how Docker functions in order to export that data to the host machine, whereas this can simply peer in and extract the information for you.
So when we take a look at VMI from a consolidation and scale perspective, it's rather attractive if you have a hosting perspective into virtual machines. If you have large numbers of them in parallel. Customers themselves often struggle with the way that clouds are deployed, simply because they're unfamiliar. Clouds are structured around deploying workloads that are instantaneous, that are self-contained, that are pre-configured. They're not necessarily built to bridge the gap between virtual machines and the actual underlying architecture. But certainly customer expectations clash with the idea of an external monitor. Some cloud providers install an agent to collect information. Some actually require root level permissions to monitor. These are options, but I think that it's more elegant when you have an additional means of monitor that isn't necessarily so directly invasive to system configuration. From a support perspective, if the VM isn't accessible in any way, it's quite attractive to say, oh, you just misconfigure your network interface, because you can see that from the kernel memory. So, generally speaking, we have a lot of use cases where this might apply. You can observe running processes. You can alert when they're not running. These are tools that we already have. They're familiar already. It's just moving the observation to a different place. Log extraction, observing open ports, active connections, and so forth. If you have hosted infrastructure, you want to minimize the amount of execution time that you've wasted running your management and monitoring infrastructure. Black box VMs become more transparent. Now, there is certainly a liability perspective about crossing that boundary. It's a spectrum. Sometimes you really want to be aware when a VM is misbehaving. Sometimes you want to provide that information to your customer. With private clouds, you can do many, many different things. You can apply workload balancing. If you know that a VM is running a database, it's an exceptionally simple thing to change its actual CPU allocations. Similarly, you can take some integration beyond. You can take a look at running processes, the open ports that they have, listening ports, extract that, and automatically configure your firewalls. Risk assessment and mitigation is a certain approach that can be pursued because you have the ability to take a look at all of the running processes, all of the GUIDs of your binaries, map them to CVEs. You can determine whether patches have been deployed and assess things in a way which isn't typically attainable. Now, existing tools are something that is worth discussing because VMI isn't a new field. It's just one that hasn't progressed at a rather speedy rate. Richard Jones at Red Hat, who you may be aware of as the guy who built libguestfs, some time ago actually built something to list processes in virtual machines. Exactly the same concepts that we're talking about here, using libVMIs, or libvirts XS into VMs. Now, QEMU is wonderful in many respects, but reading registers and reading memory addresses via a text interface that you have to convert into actual values is not necessarily a wonderful thing. It didn't go very far because it's a difficult task. Now, recall, volatility, memory eyes, these are things which are very common in the forensics community, but much like Linux crash, they're built to rip apart a memory image and get into the state of a system. But again, from a security standpoint. The tools that they provide, however, enable some rather interesting access into a virtual machine. They have profiles for memory images. And if you take a look at that, you don't necessarily need to deal with Dwarf or PDB. It's self-contained JSON, immediately accessible for use at a different scale by different developers at a different level of skill. So the field here is rather wide open because the obsession with security for VMI has actually been somewhat problematic. Not many people outside of the security world make use of it. We certainly feel that the accessibility of systems like volatility have simply been focused on the different audience. System administrators don't feel the need to use them. Recall is an interesting one. Google uses it across their infrastructure to acquire memory images and apply them through their own rules. But again, it's more of a point-in-time analysis. It's not necessarily live. These are things which will certainly help us to move forward. Now, libVMI itself, which Tomas mentioned also, is a library which is an abstraction layer. It's something that may have come up before from the Zen Access perspective. It's got a very long history since 2011 and prior to it in 2008. Because it's hypervisor agnostic, it's actually got drivers for a variety of backends. You can read-write memory. You can have caching for translation of addresses. You can read and write CPU registers. You can use VM events to obtain actual point-in-time notifications of system state changes. Single step, has some awareness of P, and binary formats like ELF are certainly in the future. Now, actually making use of this is really where I think it's helpful to have some demos, so that's what we have here. Did that come up clearly? So we have a CentOS 6 VM right here. It's not doing anything, but we're going to show reading the kernel buffer, the dmessage. It's here. I mean, it's nothing particularly interesting, but being able to see that from outside of the virtual machine is itself rather interesting. We can push it to Splunk. We can push it to any log aggregation system. Similarly, we can take a look at a Windows virtual machine, which is here, and watch what processes are running at the moment. And certainly in the background here on this screen, it's not necessarily pleasant to see, but we have 20 some odd processes. Explorer is the last one in the list at the moment, but if we run calc, for example, you should see that pop up and change. See, it's It's right there. Now, it's easy to bridge the next gap into other system tools. Zabbix, Xenos, any of the other systems that might be in use to alert on processes stopping or running. But we have a Splunk example here simply to consume some of the data. Perf information taken out of the virtual machine shows that these are the top readers of disk in this example. Average read of a meg or so for Explorer. Memory consumption by these processes sorted by top to bottom. Processes frequently seen, number of virtual machines being observed. The idea mostly is that we have access to these facilities. We have access to memory. It's just making use of them in a way that's consumable by other systems that's really the goal here. We needn't be preoccupied with rootkit prevention. It's certainly our goal at Zentific for other purposes, but it's a far broader field. We have all of this data at our disposal, and we have hypervisors there to help us get to it. It's a matter of making use of it in a consumable way, and hopefully it's something that people are more likely to try. Oh, yes, sorry. So, to recap, VMI doesn't go purely into the security bucket. We have to think of it as a much broader concept. We have opportunities for integration. Sysdig is a great example of a system awareness tool. System tools which use ftrace, ptrace, so forth. Those are tracing functions which would easily be deployed in a virtual machine inspection context. I'm sure that all of them can be adapted quite readily. Finesse in cloud deployments is something that I'd certainly like to pursue to improve scale and decrease complexity, and certainly make containers, as they become more lean and stripped down, be more visible outside of their confined area. Now, I'd recommend trying libVMI. It's certainly a low-level tool, but it makes use of recall profiles. It makes use of a variety of facilities which are currently available, and we'll be releasing some tools like the process listing, GUID listing, crossing the boundaries from the actual binaries themselves to debug data and so on. Do we have any questions? Yeah.
Does kernel address space layout randomization cause any problems?
The question was whether kernel address space randomization causes any trouble. And the actual answer is no. Because in the kernel, we have full awareness of the memory regions. We know where they start and where they end. ASLR is wonderful from a process-confined perspective, but if you're outside of that domain, you're not actually impeded by it. It does make you give pause on some level because all of the information is there. ASLR, let's be honest, has not been a fantastic, successful tool. It gets you only so far, and then you search for some data and off you go. You can still break an application. Yes?
Let's say, hypothetically, everyone decides to adopt this.
Mm-hmm.
Do you think there would evolve another policy layer to cover our debugging?
So we have a question here about whether, if people were to adopt VMI, we would see the evolution of another policy level to control debugging and access into virtual machines. Now, to some degree, we already have it in Zen. That's XSM. The slide that we were showing earlier about XSM isolating domains from one another allows you to apply some degree of policy. It's not deep. I'm sure there'd be another layer on top necessary. As with all debuggers, you have privileged access, and it needs to be governed carefully. I'm sure that that is an absolute necessity. It's certainly not something that you want to deploy without some careful thought. I mean, certainly if you have hardware security modules where you keep your crypto keys and so forth, you have a certain higher degree of comfort, but you have adjacent virtual machines executing next to each other. There will always be possibility for overlap, exposure of data. We see that all the time, whether it's a silicon bug, microcode bug, hypervisor bug. These things will happen. But I'd say that the trend is encouraging in that all of those avenues are getting closer and closer and smaller and smaller. Any other questions? Okay, thank you.